Hey, welcome back. Reactions. So we're going to be talking about a class of reactions called single replacement reactions. You're going to be figuring out what the heck happens at the end of the reaction. What are the products? So the reactants you'll be given, products you're going to give me. So what does a lot of this stuff mean? I'm just going to kind of lay it out for you in very simple terms. I'm going to use letters of the alphabet. This is an aqueous, aqueous reaction. And what that means is the reaction is occurring in water. So this reaction is taking place in water. Okay, so that's pretty straightforward. If you want to use the upmarket term, use the word aqueous reaction, or you can say it's taking place in water. Now, the reaction is one in which one element replaces a second element in a compound. So you've got a reaction with an element. This is an element. Okay, and this is reacting with a compound. And so that one's going to be the cation, and C. That's going to be the anion. So remember, this whole thing here is a compound. So again, in a single replacement reaction, an element is reacting with a compound, and this produces an element, B, but it is a different element. It is this B that is now an element, and A combines with C right here, forming a new compound. So this is a characteristic signature of a single replacement reaction. There are a few caveats to this, and I'll talk about them in a minute. But this is how you ID a reaction, specifically a single replacement reaction. Imagine for a second B and C compounds are at a dance. A comes in, taps B on the shoulder, and B has to leave and go and sit down. And A now is dancing with C. That's one way of looking at it. So think of prom. Now, the caveat is this. Element A has to have a higher ranking than B. So element A has to have a higher ranking than B, which is also an element. Okay, and the rankings will be given to you. So this is also classified as an oxidation reduction reaction, but we're not messing with that right now. I want you to learn this at the present time as a single replacement reaction. The technical term for that ranking is called the activity series of metals. That's what this is called. The rankings is not called rankings, it's called the activity series of metals. And basically, as you go down there, it has decreasing reactivity, the metals do. And this whole thing is called the rankings are called the activity series, and those will be provided to you. The specific example that I'd like to start with here, aluminum reacting with copper chloride. So aluminum, which is a solid, so it could be just foil, or it could be an aluminum pellet. Foil works great for this reaction. So if it reacts with copper 2 chloride, okay, and remember the copper 2 chloride is aqueous because this reaction is occurring in a water-based environment, an aqueous environment. When these two react, you end up with the aluminum kicking the copper off. That's what happens. So aluminum kicks the copper chloride off. So that's what you need to be observing, and that's how you can tell a single replacement reaction. So the aluminum, when it is introduced into this environment with copper chloride, will actually displace the copper. So it becomes aluminum chloride, which is aqueous, and the copper is no longer an ion now, and it becomes an element. It's solid. It is brown in color. If you're not familiar with copper, it is a brown colored material. Let's see if I can find you some. Not sure why I have it in my study, but that's what it looks like. So you start out with aluminum. It reacts with this chemical right here. You put this aluminum in here. It's a pretty It's a pretty exothermic, gives off a lot of heat reaction. And when these two react, the copper turns, this is an ion, it turns into elemental copper, which looks like this. Let's see if I can get it to focus. So that's elemental copper. This is copper in solution, this gorgeous color. So what a single replacement reaction does is it fishes out the copper as an element, and the aluminum goes into solution. So that's what this reaction is going to do. So let's just make sure you're clear on these are the reactants, and these are the products. I want to make sure that you are squared away with what is going on here. Is a piece of aluminum, looks like this, the foil. The copper chloride, it's actually a slightly greener color than this, is actually made up of two sets of ions. So you've got the copper. I'm representing the cation with this card. And the chloride component is represented with these blue cards. So there are two anions for every cation, as you can see here. And this right here is the copper chloride solution. So this is the solution that is aqueous. So when the aluminum comes in here, it reacts and it forms, it kicks this copper off, but interestingly, aluminum loses 3 electrons. The product of the reaction, one of the products at least, and this is a solution, and this is aqueous. Plus, you end up now with a copper that is solid. So your copper that started out being a cation is now has gained electrons from the aluminum and become the element copper. The element aluminum actually lost electrons and became an ion. So it started out as an element, became an ion. So just to make sure you're clear on this, so aluminum starts out neutral, okay, but then it reacts and it becomes aluminum 3 plus 3 electrons. Copper, on the other hand, was sitting like so, and at the end of it, it gains 2 electrons and becomes copper element. And this is aluminum, the element. So this starts out as a card, gains electrons and becomes copper. Aluminum becomes aluminum 3 plus, and it gets rid of 3 electrons. So it's important to be able to understand what's going on here. So the copper grabs 2 electrons, becomes an element, but all of this occurs because aluminum has a higher ranking than copper, and as a consequence, aluminum can kick copper off. So if aluminum were lower than the element over here, so let's say this was lithium, this reaction would not occur. To balance this equation, we have to balance this, by the way, because the basis of this is the law of conservation of mass. The other important thing is we cannot change any of these subscripts. The only place we can add numbers to is in the front of these molecules or elements, but we cannot, compounds and elements, but we cannot in any way change the subscript numbers. No can do. Chlorine, write it in the same exact order, folks. Copper, chlorine. If you look at this, aluminum is 1, aluminum is 1, copper is 1, chlorine is 2, copper is 1, chlorine is 3. So right away you can see that there's a problem here. So you've got to try and make these two numbers the same. So if you multiplied this by 2, you would end up with 6. And if you multiplied this by 3, you would end up with 6. So that works. The important thing here is that whatever the multiplication factor is, so we started out with 3, we multiplied by 2. That 2 is going to need to make its way in front of this compound, and that is called a coefficient. If there is no number written in front of a coefficient, it means it is 1. So there's a 1 here, there's a 1 here, and there's a 1 here right now. So we just popped a 2 on here because 3 times 2 is 6. That works great. However, the 2 is also going to affect the aluminum. Okay, it's not just the chlorine or the chloride ion. It also affects the aluminum. So we are going to multiply this right here by 2. So now we end up with 2 aluminum. And the reason for that is because right here, the 2 applies to this as well. So we've got 2 aluminum. So we need to multiply this aluminum by 2. We're going to do that. Okay, and these guys are balanced now. Works. Now let's take a look at what happened here. The chlorine, the chloride ion, we multiplied it by 3. So this 3 needs to make its way in front of the copper chloride right here. Remember, there's a plus over here. I better make some room for that. So there's a plus here. The 3 goes in front of the copper chloride because that 3 doesn't just apply to the chloride, it also applies to the copper. And this becomes the coefficient, so the 3 also applies to the copper. We're going to cut that out, write a 3 here. We've got 2, that's balanced, that's balanced. We just need to get the copper to balance, so we're going to multiply this copper by 3, and that's equal to 3. We're going to take this multiplication factor, run it right in front here, bing, bing, done. So now the ratio is 2, 3, 2, 3. So we've got 2 aluminums, 3 copper chlorides, and when they react, you will end up with 2 aluminum chlorides and 3 copper atoms, or 3 moles of copper. You can represent this in multiple ways. In chemistry, we represent this as moles. So how you would say this is 2 moles aluminum reacts with 3 moles copper, 2 chloride, and it forms 2 moles aluminum chloride and 3 moles of elemental copper. So please remember, this is not the same copper. This is 3 moles elemental copper. So this is the element copper. It is not to be confused with the cation that is over here. So that's how single replacement reactions work. I hope that was helpful, and I'll see you in the next video. Bye, guys.